Hello everyone. Today we are gonna make a parameter example, and the main purpose of the lecture today is to make an analysis in 2D, create a path and get more experience on parameters. We have a sample that has really simple geometry here, as you can see. A steel bar with 200 gigapascal Young's modulus and Poisson's ratio is 0.3 is loaded as shown, and the bar is 10 millimeter thick and its same dimensions are given in millimeters. Now you can see the 3D version here. We can analyze it in 3D because it has no complex geometry and has a small thickness. But we will learn how to analyze in 2D. Why we are making analyze in 2D? The first and the most important reason is to reduce nodes number and the elements number. So we can reduce the analysis time. I mean solving time. We can get the same results in less time without too much effort. How can we decide we'll use 2D or not? When you look at the front face, if you extrude it, there will be no changing along the extrude. I mean, there is no difference between 3D and 2D beyond thickness. Let's assume we have here a hole with a diameter of 10 millimeter and another hole in the same center with a diameter of 20 millimeter. And assume the depth of 10 millimeter hole is 30 millimeter and for the other hole is 15 millimeter. So we don't have the same surfaces along the width depth of the sample anymore, right? I mean, there are differences on between the surfaces. We should prefer 3D for this kind of bodies. For simple geometry that we have, we can prefer 2D. Now, let's look at the boundary conditions. It says that assume the left edge will be fixed and apply a tensile force with a value of 50 kN on the right edge and find maximum stress and deformation as results. Find maximum stress and maximum deformation on the dashed line, which we will create a path here. After that, we will make an observation of the changes in maximum stress and maximum deformation by decreasing the dimensions of the results. We'll set a parameter for radius and examine the changes in results. Now let's look at the steps. Firstly, it says define materials. Okay, actually we can start with let's get started by starting workbench and double click on static structure. Check the unit systems before we forgot set it to millimeter. Go inside of engineering data. What were the properties of materials? 200 gigapascal and 0.3 for Poisson's ratio. When we look at the structural steel properties, you will see the same properties with our sample. That's why we don't have to define any materials. But I will define a material to get used to it. Derive isotropic elasticity in the material that you defined, or you can just double click on it. Fill here the yellow area as 200,000 megapascal or 2E5, like that. For Poisson's ratio type 0.3, we defined our material, which is the same with structural steel. So let's close here. After that, create a geometry with design modular. Now, before starting design modular, don't forget to change the analysis type from 3D to 2D. This is really important thing. If you forget it, you have to start from scratch. Now we can start the design modular. While it's opening, let's look at our geometry. We have 100 millimeter vertical line for the left edge and 200 millimeter horizontal line for the bottom, and we have got a radius. It will be easy to draw this. Alright, design modular is opening, and the first thing that we will arrange is to change unit systems from the meter to millimeter, and also make sure degree is selected instead of radian. Let's work on XY plane, add a new sketch and look at it. Now let's switch from modeling to sketching. Select the polyline command and start drawing on the center. You make sure you see P before clicking on the center. We are gonna going that way as horizontal, and after this way as vertical, and again horizontal to the right and vertical to up, horizontal to left, vertical up, and horizontal left, and you need to see C for the center, and let's close the sketch. After right click and select open. And now we need to give dimensions from here. Select general command and start to give dimensions. V1 is 100 millimeter, and then V2 will be 50 millimeter. H3 will be 100 millimeter. With the same way, horizontal 4 will be 100 millimeter here. Okay. For the last step, let's give dimensions here. Oh, sorry. We need to define V5. V5 is 25 millimeter. We'll give a radius now. Go modify section and select fillet. And left click on the edge that will have a radius. Let me zoom in here to see it. Go dimensions and select radius to give dimensions to them. And V6 is 15 millimeter. Look at the other values is changed automatically. We need to give a dimension here as 100 millimeter. Okay, the geometry is ready now. Let's draw it. If we will have a warning with given dimensions, that means our geometry is ready. Okay, we got it. Right click and click cancel. Okay, we did it. Let's go modeling section. What should I do now? I need to create a surface from this sketch, and then to create a surface we need to go concept command and select surfaces from sketches. We need to select the sketch and apply it. After that we will generate it. Uh, the geometry will be created, and the geometry is created as you can see, so we can close the design modular. We are okay with the design modular, and now double click on model to go model section in mechanical. While we are waiting, let's look at what we are going to do in the mechanical section. Mention with default settings and apply boundary conditions. The boundary condition was the left edge is fixed and the opposite face have tension load. And actually, after meshing with the default settings, after that, let's try to get final mesh to see mesh options. Uh, we need to see these options step by step. Okay, now we are waiting for mechanical section. Also, by the way, we will get better mesh with changing default settings. So we will not use mesh tools for this level. Okay, I think it's ready. No, it's not ready. Okay, our geometry is shown as a surface here. And let's look at the geometry from here. You can, you can change its name. You can give a name that you want. We have to change the thickness from here from 1 to 10 millimeter because the thickness of the beam is 10 millimeter is given for this example. We also need to define the material here in the assignment section. Just assign the material that we created. By the way, you can see the properties from here like volume, mass, the moment of inertia, centroid coordinates, etc. And the materials that we defined here and coordinate systems here, since we don't create a coordinate system, there is only global coordinate system. Firstly, let me generate a mesh with default settings. Okay, this is the meshed surface with defaults. To get finer mesh, go sizing and use adaptive sizing from no to yes. Switch it to yes. We'll arrange resolution values again. Let me increase it to the end, which is 7. We will get smaller elements right now. Okay, as you see, there are smaller elements. And now we have 4,637 nodes and 1,458 elements. I think that's enough for us. Now we need to apply the boundary conditions. We'll apply the boundary conditions now. First, we will use fixed support for the left edge. From here, select the fixed support, and it wants us to select a face. I will select an edge, that's why select mode should be edge. Select the left edge and apply it. Now we'll apply a force. Pick force command, select the right edge, and apply the geometry. Switch vector to components, and we'll apply a tension node, so it should be on positive x-axis. And then I think the value was 50 kilonewton. You can see the way of the force here. You see the direction. Let's say so. Now to check if we have any problem. We need to get a green tick. Okay, we have a green tick on solution. That means we don't have any problems. Now, what was the problem saying? Find total deformation and equivalent stress. On solution, under deformation, total, and under stress, pick equivalent stress. Let's click solve and wait for it. Okay, the problem is solved. Total deformation is 0.07 millimeter, as you can see. You can watch the animation to see how deformation is happening. From here you can switch to the true scale, and then to get more smooth shape, from here you can switch smooth contours, and also from here you can hide mesh. We've got a better view right now. Let's switch auto scale, which is an exaggerated view. Let's check what is the stress value. It's 172 megapascal. Okay, let's examine the value as we did before. Let's go engineering data section to see tensile yield strength. It's 250, it should be 250 megapascal. Uh, okay, here, 250 megapascal. So we need to give a command according to the solutions. 250 divided by 172.69 equals 1.44, which is our safety factor. You can improve the design as we did before. You can determine the safety factor too and optimize it. What was our next step? And it's create a path on the dashed line and see its results. Okay, you can see the dashed line here at the end of the radius. Uh, let's let's see how we create a path. Click on model and find construction geometry on top, or right click on model, insert construction geometry and select path. Now, first we need to define the start point. And let me tell you that if you can create a coordinate system, you can use it here. But I haven't told it yet. That's why we don't use coordinate system right now. We will use the locations. And on location section, you can select the location as a start point. Let's switch select mode to vertex and select this point as a start point. Let's assume we can select the location. What will we do? We can give coordinates from here. Since the geometry is simple, if we look at it, we can find the locations. The horizontal line was 100 mm and it goes right 15 mm with radius, so x equals 15 mm. Or 15 millimeters from radius and it goes up 15 millimeter more, so y equals 75 millimeter. As you can see, we use these two options to determine the locations. And now you can change the path's name if you wish. Let me change it. Let me check what was the problem. Find the maximum and stress on this path. And okay, to find the stresses on this path, call stress and select equivalent stress from here. We need to switch geometry selection to path. Also, we can select the path that we created and then you can see it here. Now, right click on the solution and select evaluate for results to get to its results. Okay, solved. We can give a name on it like that. Now we can see the stress values on just this path. These values represents the path values. You can open the maximum and minimum props. Let me switch my select mode to single select and zoom in. Okay. And now let's compare the maximum value with others. As you see, it's on the almost same point. Now the next step is to create a parameter for the dimensions of the radius. We need to set parameters now. We already learned this with last long video, right? Let's go back to design modular to set a parameter. Edit geometry in design modular. There were input parameters and output parameters. Firstly, we will determine the input parameters, which value will be the input parameters for this example. right? The radius value will be input and the stress value will be output. If you want, you can add the safety factor to get more experience on Ansys. I won't do that for this example. And now let's find the sketch under the tree outline. Find the radius value in details view and click the box next to it. Give a name that you want. That's okay, we can exit from here and double click on parameter set to open it. Here under the input parameters, the radius value is set as 15 millimeter. Now we need an output parameters to select this. Let's go to mechanical. Click the equivalent stress and click the maximum. Click the box for maximum. Click the deformation and click the box for maximum. So we have two outposts as P2 and P3 that I want to observe with correct units. And then from here, we will give values manually. What was the question? Okay, we need to reduce it. Let's say 12.5, 10, and 7.5 millimeter. Okay, if you want, you can increase the numbers also. And to get the results, we need to click update all design points from the left here and click yes. You can open the process to see what's going on. And I'm stopping the recording here. I will continue when we get the results. As we expected, when the radius is decreasing, the stresses are going up and also deformation values are going up. In fact, uh, actually, when the radius is 7.5 millimeter, the stress value is so close to 250 megapascal. When the radius is increasing, the stresses and deformations are going down, as we said. Uh, in this video, we got more experience with parameters. We saw how to create a path and how to analyze in 2D. I hope you got the difference between 2D and 3D analysis. When should we analyze in 2D or when should we use 3D geometry? I hope you got that. If you want to go ahead with this problem, you can create an input parameter for the safety factor and yield stress, and after that you can find the best optimized value for the radius. And actually, let me show you where you will do it. From here, response surface optimization, just give it a try. Alright, that's all for today. See you next.